degrees of freedom. What is degrees of freedom? If you look at a spherical object, if you look at a spherical object, you will see let's say this object is moving along a straight line. Along x. So how many coordinates do I need to explain this motion or explain its configuration? I would just need only one coordinate, that is x. Right?
Yes, sir.
If the particle is moving along a plane, if this is any plane, if the particle is moving along a plane, so this is our the same sphere which is going like this, then it is going this way, then it is coming this side, finally like this, and then finally stops here. How many coordinates I will be needing? I will be needing two coordinates. One will be the x and another will be the y. And if the same particle is moving in 3D, for example, if this is a box, this is any kind of a box is here, the particle is confined in this box like a gas molecule which is confined inside a container, and it is moving randomly in all possible directions throughout this volume. There is no specific order it is moving. So it is going out in all directions. In this case, we will be needing 3 coordinates. 3 coordinate is needed to explain his motion, to explain his configuration or explain his explain the system. 3 coordinates, namely x, y, z. You would need to explain it. Whether it's velocity, whether it's the position, you need 3 coordinates. In this case, you only need 2 coordinates to explain it. In this case, only 1 coordinate x is enough to explain the situation. That means the number of independent quantities or number of independent quantities or coordinates needed to describe a system, to describe the position and configuration of a system. Here will system, because one particle is also a system, 2 particles, 3 particles together is also a system. Of a system is called degree of freedom. It's called degrees of freedom. Let's see some degrees of freedom. So how would you do it? Let's say if we consider 2 particles, a 2 particle system, let us not join them first. This is one particle, this is another particle. This particle, all of them individually, this one individually will have 3 degrees of freedom, x, y, z. Similarly for the particle 1 and particle 2, both will have 3 degrees of freedom first. And if they are fixed, and if the two particles remain at a fixed distance from each other, then there is one definite relation between them. That means I'll join them, they are at a distance r from each other. So this is one more relation between them. Therefore, we see that because of them one joined, it becomes a constant. In one particular, one of the degrees freedom will be lost in this case. So the number of coordinates in this case required to describe the configuration of system will reduce by 1. That is, each particle individually you need 6 coordinates x, y, z to explain it. Okay, so it has 6. But as it is joined by 1, then 1 get lost because you are being fixed. So that you cannot, that one particular thing you cannot use it. For example, the x1. In this case they are joined like this way. So the x coordinate will be same for, it will be dependent on each other. That means we denote by 1. So that means 5 will be the, 5 is the independent coordinate, independent systems we need. 5 is the degrees of freedom of the system, of this two particle system. So in general we can say number of degrees of freedom of a system is equal to the total number of coordinates required to specify the position of the particles, the constituent particles, minus the number of independent relations. Remember, we are using relation here. What this is one relation. Number of independent relation existing between the particles. So degrees of freedom F would be 3n minus k. So what is it? Total number of coordinates required to specify the position of the constituent particles minus the independent relations existing between them. In this case there is only one relation. Now if I consider for example, degree of freedom of a two body system, if I consider degree of monoatomic gas, for example, for a monoatomic gas, for example, in which like helium, example, let us see with an example, degrees of freedom F for monoatomic gas. Let's say example, only one, a single atom. Example would be helium, then neon, etc. So in this case there is only one, a single atom is there, a single point mass. There is only single point mass present there. Therefore it is capable of rotating about any axis, like this, sorry, not one more axis is here. It is capable of rotating in any axis. It is capable of moving along any axis. It can go this way, it can go this way, it can come this way, in all direction it can go. Therefore its degrees of freedom F would be 3 into 1. Is there any relation? There is no relation among the 0. So that means it is 3 degrees of freedom. Let us see degrees of freedom for diatomic molecule. So similarly, degrees of freedom of diatomic molecules. Example O2, N2 and so on. O2, N2, H2. So we are looking at the mechanical configurations. So if I look at the mechanical configuration, every oxygen molecule, O2 molecule, they are fixed distance apart. So this is our first oxygen. They may have different bond length and bond separation, dipole moment and so on. Let us consider to be as a, this one I've already done, but again let us do it. So they have been held together by this one. This is called the dipole moment, which we will see in later. They held together by some kind of rigid support force between them. So as a result, the set by a fixed distance. So what they can do, they will have a center of mass also. So they can rotate like this. They can also they can rotate in this way, no problem. They can rotate in this way, right? So 1, 2, 3 I can see. They can also go by. So there are 3 translatory motions. There are 3 translatory motions. First is they can go like this. They can come this way. Then this is X, Y, and they can go up and down, whatever. 3 translatory motions. It is 3 translatory motions. And 2 additional degrees of freedom it has. What are they? Rotational. You can see if you rotate, this is the way it can rotate, and it can rotate this way, right? It can rotate, but then it is the same thing as like this. Rotating about this axis and this axis is same thing only, right? This and this is same. They are same thing only, but rotating about this axis is different, right? Therefore, what we can say, the degrees of freedom, it has two rotational degrees of freedom. To rotational F, I am just writing F to understand. Therefore, and what is the relation holding them?
So 1.
1. Therefore, F would be 3 into 2 minus 1. That gives me 5. Got it? Do you understand? Now at high temperature, say around 6000 Kelvin, diatomic molecules also vibrate. Diatomic molecules starts vibrating. So they have two additional degrees of freedom at high T. Got it?
Yes, sir.
So, I mean to say here one thing. Yeah, you see the rotational thing, no? We cannot consider this one. We cannot consider this. We have to consider this one, and we have to consider this one. This is so they are fixed only to each other. Okay? Individually they cannot rotate about this. They have to rotate together to do it this way. Okay? So in this case it is not considered. This rotation will not be considered, but this will be considered. Okay? So now let us come to the triatomic molecules. For triatomic molecules, what do I mean? This is one molecule. Okay, degrees of freedom for F for triatomic molecules. So for triatomic molecules, we have 3 particles which are fixed like this. What do you think in this case? N is number of particles equals to 3. What is the relation? How many relations are there existing between them? K equals to 3. How many degrees of freedom? It can have what? It can have 3 rotational, 3 translational, right? It can have 3, the molecule has 3 translational motion, 3 rotational, right? And so 3 translational, look at this case. We had 3 translational and 2 rotational. That's why it is 3 into 2. So in this case, what do you think? I'll write here 3 translational, 2 rotation, 3 rotational. How 3? How 3? Because imagine this is the plane. This is the plane. This is the axis. This is it can rotate. It can rotate about this axis. It can rotate about this axis. All are different, no? Right or not? So it will have 3 different. In this case, so 3 rotational F. So total F would be 3 into 3 minus relation is 3. So 9 minus 3, that gives me 6 degrees of freedom. Okay?
Yes, sir.
These are case for non-linear. Remember, non-linear like this. So for linear molecules, here it will be clear. Linear molecules means we can have system like this. These are all linear molecules. And best example would be HCN. Okay? Or CS2, CO2.
Yes,
COO. In this case, what do you think would be the degrees of freedom? In this case, it is HO2, means this is O, this is H, this is H. How many degrees of freedom do you think in this case it will have? Look properly. It has, the 3 things can move along straight lines, right? So rotational, how many relations between them? These things can rotate here, can rotate here, okay, and also can rotate. Got it? But how many relations does it has now? And also 3 individuals. So in this case we can see F would be equals to 3 into 3 minus how many relations? 2. 1, 1. That gives me 2. So 9 minus 2, how much? 7. So these are for linear molecule and that is for non-linear molecules. Got it? Let us come to equipartition of energy. So the relation between the degrees of freedom and energy is established by the equipartition of energy. So it states that for a system in thermal equilibrium, in thermal equilibrium, the energy is equally distributed. What I'm writing? The energy is, that is available energy, is equally distributed. Equally distributed among the various degrees of freedom. That is why it is random. It is spinning also, it is moving also, it is going left also, right also, down also. Do you understand? Got it? Indirectly it is saying, why is that random motion? It is because of this. Distributed among the various degrees of freedom. And the energy associated with each degree of freedom per molecule is 1/2 kb kt, or Boltzmann constant, into T. So K is the Boltzmann constant, T is the absolute temperature. How can I prove it? It can be easily proved. We know the kinetic energy E is equal to, as we know, 3/2 kT. So this energy of a gas, how we have seen in last class, is at half m root mean square velocity into 3/2 kT. Right? So root mean square velocity, this can be written as Vx square plus Vy square plus Vz square, all mean. Okay, all mean square. Similarly, kinetic energy will be written as what? Average root mean square, average kinetic energy will be how much? M V mean square half m Vx square plus half m Vy mean square plus half m Vz mean square, so on. So we can write like this. Therefore, so this makes, so as the molecules are in random motion, so they are in random motion, so what is happening? The average kinetic energy of each molecule along the three axes will be same. So we will write this half m Vy mean square, half m Vz mean square. This is y, this is x. So as they are equal, what can we write? So this can be written as divided by 3. So we'll get this as, if we take the average divided by 3, so we get this E will be 1/2 kT, because this is the per axis, it would be per degrees of freedom, this one. Therefore, hence proved. This is law of equipartition of energy.